Hi, I'm Leyland Andao, and this is the second part of my final exam report about stochastic differential equation in susceptible infected susceptible epidemic model. We can recall from week 14 study guide the lesson about the SIR epidemic model with vaccination. The ordinary differential equation for SIR epidemic process has the form derivative of S with respect to t is equal to negative beta times Si all over n. And derivatives of the infected individual with respect to time is equal to beta times Si all over n minus lambda times infected individuals. And lastly is the derivatives of R with respect to t is equal to lambda times infected individuals, where we know S is the susceptible individuals, I is the infected individuals, R is the recovered or the immune individuals, B is the contact rate, Y or the lambda is the recovery rate, and N is the total population. Note that there is no birth in this model, and the recovery rate or this YI, which is also considered death rate for I since immune individuals are not modeled. Also, the infection rate from susceptible to infected individual is beta Si all over n. Now, the expectation vector and the covariance matrix to order delta t has the following form. Expected of delta x is equal to this matrix times delta t, and the summation of delta x is equal to this matrix times delta t, or we just call it V delta t. In a special 2x2 positive definite matrix like this, there is a simple formula derived by E.J. Allen from 1999. A formula for S where the square root of the 2x2 matrix V, S squared is equal to V, where this matrix here, S is equal to 1 over D times this matrix here, delta T, or the V delta T, where V sub 21 is equal to V sub 12. And G is the square root of the determinant of the matrix V, and D here is the square root of the sum of the entries along the diagonal. In line with that, SDE SIR epidemic model has the following form. This one, where the derivative of S is equal to negative beta Si all over n times G sub 11, derivative of W sub 1 plus G sub 12, derivative of W2, and derivatives of I is equal to beta Si all over n minus lambda I, derivatives of that plus G sub 21, derivative of W sub 1 plus G22 dW2, where S is in 0 to n minus 1, E is in 0 n minus n, and the diffusion matrix G sub is equal to G sub I. Also know that the state space for Si is a triangular region Si, where S and I is greater than or equal to 0, and S plus I is lesser than or equal to M. The boundary IO is an exit boundary. Once the infected individual reach 0, they will remain 0. Translating this SIR epidemic model process into an ETO SDE model. I don't know if I pronounced that right, but ETO SDE model where matrix B is a 2x2 matrix defined from B sub ij is equal to delta sub ij square root of P sub j all over delta sub t. Computed both from the infection rate and the recovery rate, it will become this matrix B is equal to this matrix. Transforming this to its explicit form, mangyayari na tong ganito. Derivative of S is equal to negative BSI all over N minus square root of BSI all over N, then derivative of W sub I. And derivatives of I is equal to this beta sub beta SI all over n minus delta I plus square root of BSI all over n. And nararamdaman siyang minus dito na square root of lambda I. Stochastic differential equation for an SIS epidemic model can be derived in a similar manner, yung parang ginawa natin kanina. Pero in this case, if S plus I is equal to the total population, which is a constant, then the model can be reduced to a single variable I, which is infected lang, wala nang recovery. Now, for the example, a real-life application of this SDE SIS epidemic model is the COVID-19 pandemic itself. We know that everyone is susceptible. Once they are infected, they can infect other people too. Then, once na naka-recover naman, hindi sila immune for a very long time. After some time, they can be susceptible again, which mean they can be infected na naman. So, it's basically a SIS, infected susceptible na process. So, let's say in a compound where there is a 100 total population, there are no visitors, or let's say sa model natin walang birds. So, if there's one infected individual and there's a constant 2 people in contact with everyone, which means ang contact rate natin is equal to 2, we can model a stochastic differential equation SIS epidemic model in a form this one. We know na ang beta natin yung nandito is 2. Tapos yung total population natin is 100. So lowest term magiging 1 over 50 na lang yan siya. Palitan lang natin yung lahat ng beta and n. So magiging ito na yung model natin. Now, since meron na tayong explicit form ng model, we can plug it in sa MATLAB. So maka-simulate tayo kung anong mangyayari. Okay, beta is the contact rate, B is the recovery rate, balik na tayo forward na tayo. Okay, here. Ito na yung MATLAB na ginawa ko with the formula. Isa-isahin natin. Here, beta is equal to 2 since ang contact rate is equal to 2. B is 0 because wala tayong recovery rate. Etong G is the infection rate, pretty straightforward, and is the total population, parehas ng sinabi ko kanina. Itong init is just initialization, then itong dt is for, vectors sa formula, para maging same like sila, and itong time t equals 10 is, let's say, 10 days. So, I made a 1,000 simulation, kung ano mangyayari, Okay. This is a for loop to dito, and this is while loop with conditions ij is greater than 0 and tj is lesser than or equal to time. Itong ij is the infected individual and itong tj is the time. Dito naman sa mu, makikita nyo na equal to beta, the contact rate times infected individual ij times the population n minus the infected individuals ij all over the population n plus sum of infection and recovery rate multiplied by the infected individuals. Etong sigma naman dito is the square root of the contact rate times infected individual times the difference between the population n and infected individuals ij all over the sum of population n and the sum of recovery and infection rate times infected individuals ij. So, ito naman dito is from iterative conditions lang, iterative conditions para ma-save siya. Then, etong no epidemic dito is parang rate na probability na walang epidemic na mangyayari. Okay, so tapos ito is plotting command. Now, hindi ka na mapakita yung live na pag-run ko dito, pero ang result nito is ganito. Itong graph na to, which is a beautiful graph. Makikita nyo dito, as time pass, sa day 2 is makikita nyo meron ng more than 10 na infections. Tapos day 4, parami na ng parami, and dito sa day 6 is umabot na siya between 70 and 80. Pero after that, nag-plateau na yung graph natin, which means na hindi niya talaga parang na cover lahat ng 100 na tao sa compound. Bali, nagplato lang siya between 70 and 80 na mga infected individual. So, yeah, that's my report for the SDE SIS epidemic model. Here are my reference from the book na gigamit natin, yung kay Alan, and this is one SIS epidemic model na nakita kong relevant sa report ko. So, I am Lailan Andao. Thank you for listening to my report.